Assalamu alaikum everyone. Today we have to continue the chapter number 8 and we will talk about the stream factor. Actually, stream factor represent you the fraction of the year in which the plant will remain operational. So we have to calculate what is a factor in terms of operational hours. So let us see what is we have here. Operating hours per year divided by total hours per year will give you the stream factor. So the equation here, number of days plant operates per year divided by 365. The typical value for the stream factor, it is from zero point 0.9 to 0.96. Well managed plants shut down for 1 or 2 weeks for scheduled maintenance, giving stream factor to be 0.98 to 0.96. Okay, so this is the value for the stream factor that we can actually use. It can range from 0.98 to 0.96 for the well maintained plant, or you have to see the problems, what should be the value for the stream factor for any specific plant. Okay, now let us solve this example which is about the stream factor, and we will see that what is an yearly cost for any raw material and the product, and what could be the revenue from the sales. Okay, so determine the yearly cost of toluene for the given process in chapter number 1. So there was a process of toluene hydrodealkylation process. What is the yearly consumption of the toluene? So we have to see the process flow diagram. What is the yearly revenue from the sale of benzene? And we have to see what is the revenue from the benzene sale. Assume a stream factor of 0.95 and note that flow rates given on the PFT are in kg per stream hours. Okay, so some of the information about the flow rate, it is given to you in the PFT, and then you have to calculate the yearly consumption and the yearly revenue. Okay, so from the table you can see the process flow diagram and the relevant table where you can find the flow rates of the toluene and the benzene. So from this table, the toluene flow rate, it is 10,000 kg per hour, and the benzene flow rate, it is around 8,210 kg per hour. So this is the information you get from the tables, and then from table 8.5 you would get the information on the cost of these chemicals. Okay, so you can refer this table 8.5 where you can find a list of chemicals along with their cost. Okay, so the cost of toluene, it is $1.033 per kg, and for the benzene it is 919 per kg. If you want to calculate the yearly cost for the tolling, so we can see that there are 365 days, 24 hours per day, 10,000 kg per hour, it is the flow rate, 1.033 is the cost, and then you have to multiply this one with the stream factor to get the value for the tolling in terms of dollars per year. Okay, so it is around $85 million per year. Then similarly, we have to calculate the yearly consumption of the toluene. Now, when you're talking about the consumption of the toluene, you don't need to include the cost. Okay, so 24 number of hours per day, year 365, then flow rate in terms of kg per hour. Then you can have the stream factor, and 1000 you can convert the kgs into the ton. Okay, so yearly consumption of the toluene, it can be equal to 83,200 tons per year. Similarly, if you want to calculate the revenue from the benzene sales, so you have the flow rate of the benzene, okay, kg per hour, year, and then you can have the number of hours per day, and you can multiply this one with the cost of this benzene along with the stream factor to get the value for the yearly revenue from the benzene sale. Okay, so it is around $62.7 million per year. Okay, so this is quite simple, and you have to simply go to the flow rates and the cost of each of the chemicals to get the value for the yearly consumption and the yearly revenues. Okay, now let us see some of the more things on the flow rates and the utilities, what kind of things we need to refer. So for the flow rate information, you can get the information from the process flow diagram of any process, and then you can multiply that one with the stream factor. Okay, so that will reflect that how much time was actual operational for the plant. Okay, so you can multiply this one with the stream factor. Similarly, you have to estimate the cost of different maybe the chemicals, the utilities, and the waste treatment, and there is a long list. Okay, so we have to see the table 8.3. So in this table you would see the cost of different utilities, so that would mainly like include the cost of electricity, maybe the cost of boiler feed water, high pressure steam, And maybe there will be like a lot of things like the air supply and the steam generation cost, and maybe like the refrigeration or the waste disposal cost. Okay, so all the utilities and the waste treatment cost, you can get it from the table 8.3, and the section 8.6, it can give you some estimation for the utilities cost. Okay, some common chemicals, you would go to the table 8.4, where you can see the cost of different chemicals in terms of their cost per unit energy, and also in terms of cost per unit their quantity. Okay, so let's see some of the tables also. So for example, this one 8.3 table, it can give you the air supply in terms of cost per unit, their quantity, or similarly you can have the steam from boilers, different types of steams, and their cost in terms of energy and the flow rates. And okay, you can also have like some cost on the cooling tower, water cost, and the electrical cost, fuel cost, refrigeration. Okay, so you can see most of the things that comes under the category for the utilities from this table 8.3. Okay, now let us see what are the different ways of getting the utilities on your plant. Number one, purchasing from the public or private utility. So maybe for any plant, if there is some requirement for any of the chemical, it can be supplied by the vendor or from some private company. Okay, so this is one of the way. In this situation, no capital cost is involved. Okay, so there is no involvement of the capital cost, and the utility rates charged are based upon consumption. In addition, the utility is delivered to the battery limits at the known conditions. Okay, so simply you can place an order and you would directly get the utility at your plant. Okay, so maybe you can assume that if you want to replace the catalyst, then you have to just place an order and it would be arrived to your plant. Okay, then the second way, it is supplied by the company. A comprehensive off-site facility provides the utility needs for many processes at common location. In this case, the rates charged to a process unit reflect the fixed capital and the operating cost required to produce the utility. Okay, so there could be a way in which a company is placed in the off-site facility of the plant. Okay, so there may be like the installation of a small company that can provide you all the utilities that are required for your plant. Okay, so they will provide all the common utilities at the common location, and those utilities cost depend on the fixed capital costs that were required for erecting that small unit, and then the operational cost from that unit. Okay, so this is like not a part of the company or the plant itself, but it is like the company outside the plant that would that maybe they install some additional units to supply those utilities to the plant. Okay, number three, self-generated and used by a single process unit. Now the third way is that you generate the utilities by yourself within the process. For example, if you see some gasification processes that heavily depends on the air separation unit, so in those kinds of processes, sometimes air separation units are installed within the plant. Okay, so that comes under the category of this one. In this situation, the capital cost for purchase and installation becomes part of the fixed capital cost of the process unit. So in this case, you have to install all the equipment relevant to that utility. Okay, that comes under the category of the fixed capital cost of that plant. Likewise, the related operating costs for producing that particular utility are directly charged to the process unit. And also, the utilities that are required to run that specific unit would be also considered as the utility for your process. Okay, so you have to compensate the capital cost also, and the utility or the operational cost for that utility producing plant itself. Okay, so that is the category number three. Okay, now there could be different types of utilities. For example, one utility is the fuel for the fired heater. Okay, so the what information you need for the fired heater: PFT gives process load, energy balance, but total flow is more due to efficiency 70 to 90% from the table, this one. Okay, so we can see in terms of flow rate, we can get the information from the process flow diagram, and we can also get the information on the energy requirement from the PFT. Okay, but the actual actual equipments but the actual equipments or the heaters or heat exchanger, they do not perform at 100% efficiency. So you have to incorporate the effect of the losses within the process. Okay, so you have to see the relevant energy conversion and how much is the energy wastage from the process. So you have to consider the relevant percentage and the heuristics for those particular equipments. Okay, so these tables 11.11, it will give you the heuristics about the fired heater, and there you would find the efficiency range from 70 to 90%. Okay, now fuel cost may vary widely. Okay, so you can have different kinds of fuels. Maybe sometimes you are using the natural gas as a fuel in your process. Maybe you can use some coal, or you can use some like the petrochemical, or some like oil, or like the petrol, diesel, whatever. Okay, so depending on the cost of those fuels, the overall utility cost may vary, and that would definitely affect the production cost of any product. Okay, now we can see the electricity for the pumps and the compressors. Okay, so these equipments, they usually depend on the electricity requirement. So you have to see what is an electricity cost for these pumps and the compressors. Now if you look at the information about the pumps and the compressors, you would find two kinds of information. One is the shaft power, which is the fluid power or the efficiency. It is linked with this one. And then power to drive. Okay, short power driver efficiency. Okay, so there are like whatever information you require, you have to see the relevant table or the figure, and there you would see sometimes the shaft power or the overall efficiency, and what could be the relationship between the shaft power and the efficiency. Okay, so you would find this kind of information from some of the figures that we will see. Okay, PFT usually gives shaft power, but be careful. Okay, so the PFT usually give you the information about the shaft power, but to get the actual power requirement, you have to incorporate the efficiency of that particular equipment. Okay, so whenever you make the analysis, you have to consider the losses in terms of conversion of electricity or any power to estimate the complete amount of utilities requirement. Okay, now here you can see the graph for the cost of fuel, and here you can see the years, and on the left hand side you can have the dollars in terms of gigajoule. Okay, so you can see for the coal, we can have the least cost, then we can have the natural gas trend, oil, and some other things. Okay, so you can see with the increase in the years, okay, there is usually an increase in the prices of the fuel, but depending on each of the type of the fuel, you can have different costs. Okay, so maybe if you change the fuel for your process, it can heavily impact the cost of any product also. Okay, now here we have seen that there is like a lot of utilities in the process. Maybe air supply, you have to deal with the pressurized and the dried air and different pressures here, and on the right hand side you have the cost in terms of the quantity. And then also you can have the steam from the boiler. So sometimes the process steam is required to generate electricity, or sometimes the steam is required within the process for the heating and the cooling requirement. Okay, so for each of the type of stream, you can see the relevant cost here in terms of energy and also in terms of quantity. Okay, similarly you can see the cost for the cooling water. The temperature range is given here. Electrical supplies, the cost is given here, and then similarly there are different types of fuels along with their cost. Importantly, the refrigeration processes, you can see the temperature range here and the cost required. Okay, in terms of dollars per gigajoule, and also in terms of dollars per unit quantity requirement. Okay, similarly you can have the waste disposal cost, thermal systems along with the efficiencies, and the dollars per unit energy requirements. Okay, so you can see what is the relevant information which is required by your process, and then you can estimate what is the value of the total process utilities requirement. Okay, now in the industry, you can see that there are different types of streams that can be used to generate electricity, or to run the turbines, or to run the compressors. Okay, so you can either have the low pressure stream with this range of pressure, you can have the medium pressure or the high pressure stream. Okay, so these streams sometimes you require to just like an heat exchange, so maybe the saturated stream is required. Okay, but sometimes you need to utilize that stream for getting the short work, then you need to make that stream more like superheated. Okay, so depending on the pressure level of each of the stream and the temperature conditions, you can decide that either you can use that stream for the power production or to use that stream into the process for the heating or cooling requirements. Okay. Utility stream. Large chemical complexes generate high pressure stream and use excess pressure to generate electricity. Okay, so sometimes you can have the high pressure stream within the process and you use that stream to just generate an electricity, but most of the time it is a superheated stream. Okay, and sometimes steam can be used as a drive medium for the compressors and the pumps, and you can use the steam to derive compressors or the pumps. And for the thermodynamic efficiencies for the compressors and the pumps, you can refer the table 8.5 and figure 8.7. So we can use these two tables today also in one of the example. Let us see. Okay, now the stream, as I told you, it can be used for different ways. Okay, so first one, it can be used for the heating requirement. So this one is a process stream which is being heated, and the steam which is coming here, it is being cooled down. Okay, so you can have the condensate of the stream. Okay, now whatever stream that you're using in the process, there could be different types. If you are using the steam for the electricity or the power generation, then you have to make that one superheated stream. Okay, and it should be free from the particulate and different kinds of falling material. Okay, so you have to specially prepare the boiler feed water to generate this stream. That would be eventually condensate, and it can be sent to the boiler again to be converted back into the stream. Okay, the second way, you can use a boiler feed water to generate the steam. Okay, so in that case, it could be the fired heater. So you can have the boiler feed water into the fired heater that would be converted into the steam. Okay, or here maybe you can generate the boiler feed water and use it for the conversion into the stream by using the process streams. Okay, so in this case, process streams are getting cooled, whereas a boiler feed water, it is getting hot and converted into the stream. Now here you can see the simple Rankine cycle which can be used to generate the electricity, and also you can see some of the intermediate processes here that can be used to use the stream for the intermediate process requirements. Okay, so you can have the fired boiler here which is fed with boiler feed water, and here you can convert it into the high pressure stream which can be used to generate electricity. So outlet can be at the low pressure, so that can be the input of the medium pressure turbine, and similarly you can have like the pressure reduction in this turbine to generate electricity, and that could be the input for the low pressure turbine. Okay, so this is the part for the electricity generation, and similarly you can have some parts in which you want to directly use the steam for the process requirement. Okay, so if you want to use the superheated stream for heating some of the process streams into the process, you can have some like the side pipelines in that system to use that stream. Okay, similarly somewhere you can use the medium pressure or the low pressure streams. Okay, so depending on the heating or the cooling requirements into the process, and to maximize the heat utilization, you can have the good heat integration network within the process. Okay, so this is the overall process for the utility stream, and how we can generate the electricity and how we can actually use the stream within the process for the heating or the cooling requirements. Now this one is basically representing you the cooling of the water. Okay, so you can see that for the cooling water, the maximum temperature it can be 40 and the minimum temperature it can be 30 degrees C. Okay, so you can use this cooling water for cooling the streams up to 40 degrees centigrade, and then that cooling water is fed to the cooling tower where the temperature is reduced to 30 degrees centigrade. Okay, so this one is a cooling tower. It can be forced draft or the induced draft cooling tower, and then you can have the cooling water. Then it can be either used for process user, so maybe wherever the cooling requirement in the process, you can fed it into that particular unit, and there can be like some kind of blow down to reduce the solid particles within this water. Okay, so there is some continuous blow down from any process, and then you can have the anti-fouling chemicals within this cooling tower. Okay, and then you can also have the makeup. So this one is basically representing you the cooling tower requirement. Now let us see what is the utility requirement in terms of the refrigeration. So this one is a very simple refrigeration cycle that started with the compressor, then you can have the condenser, then you can have the expansion valve, and then you can have the evaporator. Okay, so this one is the simple refrigerator that you can also see in your homes. Okay, so the condenser is basically the grill that is behind the refrigerator, and evaporator is you can take this one as the inside of the refrigerator. Okay, so some cooling is taking place here, and then you can have the compression, condensation, and then the expansion. Okay, so this one is a cyclic process, and you can see that the outlet of the condenser which can have the liquid, and after the expansion valve we can have the mixture of liquid and the vapor, and at the inlet of the compressor you can have only vapor, and at the outlet you can also have the vapor. Okay, so this one is a cyclic process, and these are some of the constraints that we need to see. Okay, now how you can actually estimate the efficiency of the refrigeration cycle. So the Carnot efficiency of a mechanical refrigeration system can be expressed by the reversible coefficient of performance. Okay, so the coefficient of performance, it can give you an idea that how much any refrigeration cycle can be an efficient one. Okay, so what we can see here, coefficient of performance for the reversible process, it is the ratio of evaporator temperature divided by temperature difference between condenser and the evaporator. So what we can see here, if the evaporator temperature is going high, then what would happen? If the evaporator temperature is going too high, then the coefficient of this performance, it would reduce. Okay, because you can see this T1 in the denominator high also. Okay, so as you keep on increasing this evaporator temperature, what would happen? The coefficient of performance would be reduced. Why? Because if you are getting more hot stream at the outlet of this compressor, at the inlet of this compressor, then the compressor has to do more work. Okay, so we have seen this certain like equations in the thermodynamics that if we increase the inlet temperature to the compressor, then the short work for this compressor would be highly increased. Okay, so this is the similar way of representing those equations. Okay, so if we are increasing the evaporator temperature or the inlet of the compressor, then the what would happen? The overall coefficient of performance would decrease, because of this term is also included into the denominator. Okay, so you can see this equation also. You can see this one in the form of, if the coefficient of performance, it can be a function of evaporator head load divided by work required. Okay, so if the evaporator heat load is very high, if you are having high temperature at the outlet of this evaporator, obviously then compressor has to do a lot of work. Okay, so this denominator, if you increase this term, what would happen? The work required by this compressor, okay, it would be very much increased. That would ultimately reduce the coefficient of this performance. Okay, and also you can also rearrange this equation in the form of work required in terms of evaporator heat load and the cost of performance. Now once you have this kind of equation, we can actually estimate what is the power required. Now you can also get the cost from different websites. Okay, so this is one of the website that is written here, and if you go to this website, you can see different chemicals along with their cost. Okay, so similarly, you can either consult your books, or you can search different international websites to get the idea for those costs for the chemicals. Okay, in your book, you can also find this table 8.4, where you can have the list of chemicals along with the cost in terms of the quantity. Okay, so you can have the cost for different chemicals. Okay, so the list goes on here. Okay, now here, what is the summary that we have seen, or the things that we studied until now? We can now find out the fixed capital investment. We have seen what is an equation for the fixed capital investment, what is the cost of the operating labor, cost for the utilities, cost for the waste treatment, and cost for the raw material. Okay, so if you calculate all of these things, actually you can estimate the cost of manufacturing without the depreciation involvement. Okay, so we have seen what are the equation for cost of manufacturing with the depreciation and without the depreciation. Okay, now here you would see one of the table here, which can give you the theoretical steam requirements, and if you are using some kind of turbine, then what could be the what could be the power that you can actually generate from that turbine. Okay, so here you can see that on the top line you can have the information on the pressure, and here you can have the information on the temperature, and on the left hand side you can have the exhaust pressure. Okay, so you can link, for example, this one. Okay, 4.67. What would happen if the inlet pressure is this one and the temperature is this one? Then the outlet pressure, it could be 0.69. So you can have the reduction in the pressure, and how much energy that you can generate here, 4.67 kg per steam divided by kilowatt hour. Okay, so this much is the amount of energy that you can generate for each kg of the steam utilized. Okay, so if you increase the steam flow rate, obviously you can have more production of the energy from this given steam turbine. Okay, now you can also see certain graphs that can relate the shaft power with the driver efficiency. Okay, so you can have different systems. For example, if you are dealing with the electrical system, okay, you're supplying the electricity to the motor, then what could be the driver efficiency? Okay, so you can see what is the shaft power here, and then you can have the information or the of this equation here there, where you can put the value for the shaft power and you can get the efficiency for the driver. Similarly, you can have the steam turbine and the gas expanders. Okay, so this is another way of the equipment that can be used to generate electricity. Okay, so here you can put an information for the shaft power that you can actually get from any steam turbine or the gas expander, and then you can use this equation to get the value for the driver efficiency. Similarly, internal combustion engines. Okay, you can have the value for the shaft power, or what is the requirement for the shaft power, and then you can estimate the value for the driver efficiency, or you can simply use this graphs also to get the idea about the shaft power. Sometimes you would draw the process flow diagrams and you would get the information about the shaft power. Now there you can see what is the relevant system, and then you can estimate what should be the relevant driver efficiency, and then you can have more idea that what could be the energy losses, and how much would be the utilities requirement to compensate that energy difference. Okay, now let us see what is the difference between the steam turbine and the gas turbine. So the steam turbine uses high pressure steam as the working fluid, while the gas turbine uses air or other gases as the working fluid. Okay, so in the steam turbine, the working fluid is the steam. However, in the gas turbine, it can be air, or it can be some exhaust gases. Okay, and that can be used as the working fluid. Steam turbines is basically an expander delivering torque as the work output, while a gas turbine is a combined device for compressor, combustion chamber, and the turbine executing a cyclic operation to deliver work as either torque or thrust. Okay, so in the steam turbines, you can simply have an expander where the steam is getting expanded, and then at the maybe the outlet of the steam turbine, it can be converted into the water again. However, in the gas turbine, it is like the connection between the compressor, combustion, and the turbine on the same shaft. Okay, so usually you can have the combustion in the turbine in this combustion chamber, and then the gases expand into the turbine, which is on the same shaft where the compressor is attached. Okay, so this one is all the processes are going on the single shaft. Okay, so you can have the more better process performance in case of this gas turbine. Okay, now steam turbine is only a component executing one step of the Rankine cycle. Now the steam turbines, they usually include the Rankine cycle where steam is only used as a working fluid, whereas in the gas turbine you can have the combination of the Brayton cycle and the Rankine cycle. Okay, so in the Brayton cycle you can have the combustion and the expansion of the gases. Okay, and then the exhaust of the Brayton cycle, it is usually at a very high temperature, so you can connect that one with the Rankine cycle to further utilize the heat from the exhaust gases and to get more energy from the process. Okay, whenever you see, for example, the gas turbines in the industry that is connected with the Brayton cycles. Okay, so you can have Brayton and the Rankine cycle together in the gas turbine, and in the Rankine cycle you would only have the steam turbines that would be used for producing the electricity for the process requirements. Okay, so this is all for today, and the next time we will start some of the examples relevant to this chapter. and please let me know if you don't understand anything. Okay, thank you.